What else do we need? I think that's it. Okay, so we need to find derive the equations of motion for this manipulator, which we did the equations of motion using symbolic calculations, but the issue with symbolic calculations is that as the chains become long, these equations become long. I'll show you the equations. They were like really long, right? And that was just for 3-link. So what I'm going to do next is I'm going to show you how you can do this numerically. Okay, and for that, what needs to be done is, first of all, you cannot use Euler-Lagrange to do that, because for Euler-Lagrange, you need to take the derivative of this term. And that is just not possible numerically. But when it comes to Newton-Euler, it's most certainly possible to compute the equations. If you look at the forward and backward recursion here, you can set this up using numerics, because there's no differentiation involved. Okay, so next what I did was, just to save some time, is I have set this up in an environment where you could do this with Python, like write your own code, but you could also check it against MuJoCo. There are a bunch of things. What I'm going to do is I'm going to drop in the main file. The main thing here is that there's a function called RNEA. This is the abbreviation for Recursive Newton-Euler Algorithm. The same thing I showed you on paper, right? What this code will do is the following. We set a position and a velocity. So I get a position and a velocity, and this comes from the key. There's a key saved for the position velocity. I use MuJoForward. MuJoForward actually takes the equations and it does a forward kinematic. So it computes the acceleration, but it doesn't do the integration. Okay, and so far we've only used MuJoForward. Now that we know this, next class onwards, well, 2 classes onwards, we'll actually start using MuJStep, which is the next thing to MuJoForward. I use RNEA to compute the C matrix, the Coriolis term, the G matrix, the gravity term, the sum of the two. I just sometimes, it's good because I have to, MuJoCo doesn't actually give you C and G, it only gives you CG. So I have that, so I can easily check. And then the mass matrix. Okay, and this is pi because my calculation. So what RNEA, recursive Newton-Euler, needs is the position and the velocity. Okay, so the main thing here is essentially the RNEA function, which I've coded here. And if you look at the function, you'll see that it looks very similar to the function I have for the symbolic calculation. So essentially, it's taking the same thing, but replacing the symbolic variables with numeric values. So here is RNEA. If you need to go all the way down to see the function. So here's the function. I've called it Q and Q dot for position and velocity. Now, what I need to do is, in order to do this, there are 2 things going on here. One is we have to first compute this forward recursion and backward recursion. This is forward, this is backward. And then I need to do this trick to figure out this mass matrix G and so on. So what has been done in this code is I write a function called forward backward recursion, which is in the beginning. Okay, what this function does is it takes in inputs of position, velocity, acceleration. It takes the robot because it basically needs to do the forward kinematics. And then it also needs gravity. The reason I send all these variables, in fact, the additional variables, is because I need to be able to do what this stuff does. Here I put acceleration equal to 0 to get n1, right? And so on, right? So for that, I have these other parameters which I send to this forward backward recursion. I can do this recursion with any of these variables changed. So what this code does, it does forward recursion. So initial velocities are 0. It propagates the whole thing through the chain to get the velocities, angular velocities of each link. Then I do the backward recursion to get the forces. So gravity, it's ultimately stored in force, and torque, I call the torque variable as n. So I get that. And then what I do is, remember that the torque comes from the axis. So here the axis, I find the axis. In this case, all the axes are k, but this is written in such a way that you could reuse some of the robot data, which I've never really used for MuJoCoPy in this class, but I've said it such a way that I can use robot data automatically to call this instead of trying to hand code everything. So this returns tau, but that tau is returned for a specific value of q, q dot, q double dot, robot, and g. Why I need this is because I'm doing the second step now, which is to find the mass matrix. Okay, so that is done in RNEA. Now, first I set all the accelerations to 0. So this is to compute c. So then tau c is basically q dot, q double dot. Now q double dot is 0. I also set gravity 0. So when I set gravity 0 and q double dot equal to 0, go here. Here, if you go on C, you set q double dot equals 0 and gravity equals 0. That's precisely what I'm doing here, but everything is done numerically. Second thing we need to get the CG term. Okay, now I could always compute G and add it, but I just say I want CG. To get CG term, if you go here, you'll see to get the CG term, which is C and G, all you need to do is put acceleration equal to 0. So this term disappears and you're left with only C and G. So that should be done next. So I put q double dot equal to 0. Gravity is not 0. Gravity is whatever it is, 9.81. And now I can get CG. Then to get G, all I need to do is take CG and subtract out C, which was computed here. Okay. Now, mass matrix is actually kind of interesting. We've never seen how to do the mass matrix numerically. We've used in this code, we use the Jacobian, right? We cannot use Jacobian numerically because there's no symbolic variable. So the way the mass matrix is calculated as follows. I'll write it down first, and then I'll show you the code which does it. Compute M numerically. So I'm looking at C right. I need to compute this term numerically. Okay, so what this term looks like, it looks for the 3-link manipulator, it looks like this. And then you have q1 double dot, q2 double dot. I want to expand those, but those are essentially 3 cross 1. Okay, so what I need to do is I'll put q dot equal to 0, g equal to 0. So what that will do is it will essentially ensure that c is 0 and g is 0. They're eliminated. Now, to get the mass matrix, this is what you do. Set q1 double dot equal to 1, q2 double dot equal to q3 double dot equal to 0. So if you do this right, then the net torque which you get will be m11, m21, m31. Okay, next I set q2 double dot equal to 1, q1 double dot, q3 double dot equal to 0. So I'm just setting the second acceleration to 0, and this gives me torque equals 1, 2, 2, 2, 3, 2. And then finally, set q3 double dot equal to 1. Then you get q1 double dot equal to q2 double dot equal to 0. And then this gives me tau equals the third column, 3, 1, 1, 1, 3, 1, 3, 2, 3, and 3, 3. Okay, so I need to do three calls to forward, backward recursion. Right? So every time I do this call with different values, I get mass matrix. That's precisely what is done here. So this is to compute M. I run this in a loop. I run it from 1 to NV, NV being 3. So I set the ith element to 1. Everything else is 0. I do a forward backward recursion. Whatever I get, I put it in M. I subtract out CG. You could either subtract it out, or you could put q dot equal to 0 and g equal to 0. It's up to you. It's same. It does the same thing. And then I set that back to 0. Okay, so this will give me the mass matrix. Okay, so that comes up. It's outputted here. Now there's a way to check your calculations using MuJoCo. MuJoCo has a function called there are two things. One is there's a function called full M, which gives you the M matrix. It is to be used in this form, as I've shown here. And then there's another variable called QFRC bias. So the way MuJoCo, in MuJoCo, we have M times Q dot plus QFRC bias equals tau. Okay. So this is the same as what we got, M times Q d dot plus C plus G equals tau. So we have C plus G equals Q FRC bias. So MuJoCo does not give you C and G, unfortunately. It only gives you C plus G. So to get that, you just need to take the variable QFRC bias, which is here. So I saved in QFRC bias. So I'm printing out CG, MJ, CG pi, my calculation. I have this function which will give me the difference between the two. It's an easy way to check that instead of trying to compare the two. But then the mass matrix comes from using MuJoCo function. I print it here, then I print the my version, M pi, and then I print the difference to show that they're same. So running this, okay, so it runs for a few seconds and stops, but this is CG from MJ, this is CG from my calculation. The best way to check is to look at the difference, which is 0, which means that I've got exactly the same answer as them. Mass matrix, this is a mass matrix using MuJoCo, mass matrix, my calculation. If I do the difference, it's 0. So this is just showing you that that the calculation which we did using recursive Newton-Euler algorithm is exactly the same which MuJoCo does. But we got more than what MuJoCo is able to do. It actually, we also get G and C. And the reason why you want C and G is because when we're talking about trajectory tracking or control, sometimes you want to do gravity compensation, which is subtract out the contribution to gravity. So we'll be able to do it because we have gravity, but MuJoCo, you're stuck with CG. Now there are ways to overcome that and compute G from MuJoCo. You have to do more calculations. There's some tricks you can do, but here we have a distinct advantage over what MuJoCo can provide because we have this additional term which is useful in control.